All right, so on to another problem. Suppose the average velocity of carbon dioxide molecules, which has it says molecular mass, but it turns out that MOL doesn't stand for molecule. It stands for mole, so that's a molar mass. In a flame is found to be the speed. So that's VRMS is equal to 1.05 times 10 to the fifth meters per second. And so what do we know that's going to relate the speed with the temperature?
Is that the delta V equal V initial beta T?
Nope.
What about delta V? Yeah, well, you said this. Delta V equals beta V delta T.
Oh, the V. This.
That's not it.
It's the square root 3 RT over M.
Oh, there it is.
Okay, now what's the difference in this one and this one
They have the constant K.
versus the constant R? What's the constant K?
Spring?
It was at one point.
Kelvins or constant K? No, that's the constant that we had to look up in class this morning. Right? That's what you looked up.
Nope. That's sigma, the Stefan-Boltzmann constant.
Mm-hmm.
I know they both have Boltzmann in their name for the same gentleman, but they're not the same either. The K is the Boltzmann constant, and the R is the gas constant. But the important distinction between them, they're really the same thing, but K is per molecule, R is per mole. So given that they gave us the mass in grams per mole, which of these two equations do we need?
R.
The one with the R. Okay, so we'll just put our numbers in. So we'll first solve it for T. So VRMS squared is equal to 3RT over M. Therefore, T is equal to M VRMS squared over 3R. Then we just put in our values.
Is that pi? Oh, no, sorry, wrong one. Whoops.
And what is the value for R? 8.3145.
So the only difference between these equations is that one is for moles and one is for molecules.
Yes. So Avogadro's number basically is the difference. Now, if I put in these numbers in my calculator, I'm going to get the wrong answer. Why will I get the wrong answer if I put these numbers into my calculator?
You know.
That's right. Which one is in the wrong units? Oh, you can't see. Which one is in the wrong units?
Gram.
Right. The grams are the wrong unit. What unit do I need there?
Kilograms.
All right. So I'm going to multiply this by 1 kilogram per 1,000 grams. Then I'll have the right number in units of kelvins. That seems mighty high.
It's kind of off.
And it's in a flame. It could be in the ballpark of 1,000, but not in that big. Ten to the fifth squared is 10 to the 10th.
Can I see your screen?
Divided by 1,000 is 10 to the 7th. Wow, it really does look like it's that big.
Yes, it's in there.
2.17 times 10 to the 1, 2, 3, 4, 6, 7. That is an extremely hot flame. That's very unrealistic. None of those are exactly their answer either.
Do we
Can you go back? I want to see if I can put it in again. A different answer.
Don't know.
I got a really small number.
Well, somewhere between really small and really big should be right. Okay, I'm going to pull out the spreadsheet. R equals 8.3144. 8.3144598.
Oh,
Is that
I
not?
think I got it. It's 1.95.
How did you do it?
Let's see. 1.95 times 10 to the 7.
Okay, so I put 44 and 105.
No, 105 times 10 to the
5. Oh. Okay, and then
divided by 1,000.
that's only the first part.
Then divide by 1.95.
Yeah, 1 point. I'll go with 1.95. I got 1.9448, but well, that would round to 1.94 then.
Oh,
But see, they can't round either.
I got to the 8.
The next one is one that I put on your last test, so I'm. Or the ones after this are the timed ones or the spaced. So do you want to go on to 29?
Yeah.
Okay.
and we have one more on the fine density of the.
That's on.
That's also from.
Yes.
Yeah.
It was 1.95 times 10 to the 7th, right?
Yeah.
It is something wrong. I got to the 8th, but I believe you. And mine wouldn't have rounded to 5.
Well, yeah, it rounds to 4. And I'm going to put it down here because I don't want to clobber the last line where I have it.
There it all
I
is.
did clobber it. Yay. Well, at least I can. Yeah. A room has a window made from thin glass. The room is colder than the air outside. There is some condensation on the glass window. On which side of the glass would the condensation most likely be found? So now I'm waiting for this to come over to my tablet.
Okay, let's think about this. We can
It's
do
in the
this.
inside, but whether it's because of the cool, dry air inside the room or the warm, moist air. The room is colder than the air outside. Merp?
Wait,
I
if
think
the,
it's D, but I don't
if
know.
the room is colder than the air outside,
Oh,
wouldn't it be
on
outside?
the outside.
Yeah, it'd be on the outside.
What are your key ideas that are helping you come up with that?
Because when condensation occurs when something's being heated, right? No.
Vapor.
It's warm hitting cold and
Or like
The
droplets,
amount
right?
of moisture the air can hold
Mhm.
is not directly, but proportional to the temperature. That is, as the temperature goes up, it can hold a lot more moisture. Condensation occurs when the moisture is level in the air is equal to the total it can hold. So if you start with warm air and you cool it, the amount of moisture in the air stays the same, but the amount it can hold drops. And so if you cool it enough that the amount it can hold drops below the amount that's in the air, then you have condensation. So what you're looking for in where's the condensation going to occur is where did you start with warmer air that has water in it that you cooled down to the point where the water condenses.
Outside is warmer air.
And so the glass is going to transport heat. What mechanism will the glass transport the heat through? We have the
It's
three
either
mechanisms.
convection or conduction.
Yeah, is it going to be conduction, convection, or radiation?
Radiation.
I think it's conduction or convection.
It's conduction because you're going through that solid
Oh, it's
glass. Now,
conducting
glass
heat,
is a
okay.
poor conductor, but it still conducts heat. And so you're doing conduction. You don't have convection because you don't have anything flowing from one side of the glass to
Okay,
the
yeah,
other.
that's what the
And the radiation, glass being transparent, it's got an emissivity that's approximately 0. So this never did come up on my tablet, but you're going to have then the temperature on both sides of the glass will be roughly constant, roughly the same. And so it cools down outside where it's hot. And so the air molecules or the air that comes to the window gets cooled. And then you have same moisture, but it can't hold as much and it drops out and you have condensation. So you expect the condensation on the outside in this case.
Okay.
Hey, it finally showed up.
So B.
So outside, A or B, glass.
yeah, I think it's
When the cool, dry air inside the room comes in contact, well, the dry air isn't coming in contact
it's B.
with the cold. Yeah, dry air would be silly. Dry air is not going to condense, right? So it's going to be the moist air outside comes in contact.
So the concept this one will be conduction.
This would actually be the concept is that there is conduction here because you have conduction through the window. But the primary concept is that condensation occurs when the amount of water in the air is greater than or equal to the maximum the air can hold. There's lots of different ways, the partial pressure, or, but the idea is when you have more water than the air can hold, you're going to have condensation. It's going to form droplets instead of just staying like in the gas form. And the amount of water the air can hold is a strong function of temperature. So as temperature goes up, the air can hold far, far more water. So you cool it down and can't hold nearly as much, condensation occurs.
Kind of like the greenhouse effect that you were talking about.
I don't see an analogy between them. So, shall we move on?
Yeah.
Yes, please.
I love going through these problems.
Have prior classes asked you to do this?
This is the first year that I've had these, so not an option for prior classes. why does it feel hotter on more humid days, even though there's no difference in temperature? And boy, do I feel the difference. Let's just look at each one piece by piece. So on hot, dry days, the evaporation of the sweat from the skin cools the body. Okay, so there's something that would cool the body. Whereas on humid days, the concentration of water in the atmosphere is lower. Nope, it's higher.
It's B or D.
So we can rule that out. So we ruled out A and C because it says on humid days, there's less water in the air. That wouldn't make sense. Okay, so the others. On hot days, the evaporation of the skin cools the body. They all have cools the body, so I didn't need to underline that. On humid days, concentration of water in the atmosphere is higher, which reduces the rate of evaporation, is what this says, which increases the rate. The reason is the rate of condensation is going to be proportional to how much water is in the air. And so if you have more water in the air, you're going to have more condensation. Less water in the air, you have less condensation. And when it talks about the rate of evaporation, you're talking about the two together. You have evaporation and condensation. If evaporation is equal to condensation, then we would just say there is no evaporation because the net evaporation is zero. Right? If the number of molecules leaving is equal to the number coming back in. So you have to have more leaving than are coming back in. And if it's dry out, then you don't have any coming in, you have more leaving. Well, you have the same amount leaving, but you have nothing coming in, so the net result is more leaving. If it's wet out, you're going to have lots coming in, so you have very little leaving as a net effect.
With like condensation and convection and stuff, in class you said that there's no equations for those types of.
Yeah, for convection, we have no equations in this class.
Do we have equations out of curiosity in calculus, basically?
Nope.
Oh. So no one really knows how to do that?
No, that's untrue. It's just beyond the scope of this class.
Yeah.
There's lots of things that we can do. Not so much that we can do,
At our level.
At our level. So one of my friends, she was a physics major as an undergrad, and then she went to medical school. Her son was doing an AP physics class and had a question. She was like, "Ooh, better ask Richard. I don't remember."
Mm-hmm.
And, we're going through these things. It was trying to analyze a car going over a cliff. And I was, we can use the drag equation, but it's going to require a whole lot of sophisticated work. That's not what you're doing in your AP calculus or physics class. So we'll just say it's there. What is the rate of heat conduction through a 3 centimeter thick fur of a large animal having this surface area? Assume that the animal's skin temperature is this, that the air temperature is this, and that the fur has the same thermal conductivity as air. Does that make sense that the fur has the same thermal conductivity? Yeah, because what's the fur doing? It's just trapping the air. Okay, so for this, I'm going to draw a picture somewhat similar to what we had the picture in class today. We have, here's the outside of the fur, so the fur's all in here. And then we have the skin of the animal. And so the distance between the fur and the skin, I'll just call X. And so we're given that it's 3 centimeters thick, so we have X is equal to 3 centimeters. Or old school physicians call them sonometers. I don't know why. Okay, and then we have the area, so the patch of skin here, or the patch of fur with skin underneath, it has area equal to 1.40 meters squared. And we have temperature of the animal is equal to 32.0 degrees Celsius. So we're probably not talking about for on me. And we have finally temperature of the air is equal to minus 5.0. Didn't give myself space.
So this one is the skin.
Yeah. Okay, you're right. I should use something besides A for animal since I used A for air. Thank you. Nice. Okay, so there's a picture. Now we have to think about the concept. So the first one is the stupidest question I'll ask you today. What kind of heat transfer is going on in this problem?
Conduct.
Yeah. Conduction. Right, it says it twice in the question. So for that, we have power, which is the heat over change in time, is equal to K, completely different K. Now it's the thermal conductivity
Okay.
times the area divided by the length multiplied by the temperature difference. Now, of course, this is an equation that's going to be on your equation sheet. You don't have to have it memorized, but you have to know how to use it. So we've got the equation. We've got the picture. I just take all my information from the picture, except for I need to look up what thermal conductivity for air is. This is 14.5. We better have a table. Here we go. Thermal conductivity for air is 0.023 joules per second meter degrees Celsius. My area divided by my length. The length is 3 centimeters. What do I need to put in my equation?
Meters.
Yeah. And then the change in temperature. So that's the temperature on one side minus temperature on the other. I'm just going to go ahead and put it in the form to give me a positive number because I know what direction it's flowing. It's going from the animal out. So I'm just going to put the high temperature minus the low temperature. So 0.023 times 1.4 times 37 divided by 0.0300.
A. 39.7.
39.7.
Okay, that wasn't so bad.
So this one concept is thermodynamic
So this one here is conduction.
conduction.
Oh yeah. Whoops. Oh yeah, you did ask that. Wow.
Yeah. It wasn't my toughest question, I thought. And then we have a second part to this question.
Hello.
I should know better to do anything with Brittany here.
Can I? Okay.
You broke it.
Again.
Yes. I don't know what to do. I can come over here, but
I swear.
Step outside.
I know. Never come back.
I'll be there. Well, shucks. Last time this happened, it took forever for me to recover.
What is unit for what?
That's what I was just looking at.
Excellent.
It looks like joules, definitely.
Joules times
Joule over meter. No. Joule per meter.
What about seconds?
Actually, joule over meter. No, joule over second.
There's got to be a way to recover from
Yeah,
this.
joule over seconds, yeah.
Okay. It's good that we have a plan B. Username.
Kilograms times meter squared times
Boo.
seconds to the -3.
No. What is that?
Uh-oh.
I think that yeah, or newtons times
Yeah, because
meters per second.
yeah, because Newton times meter is a joule.
That's why.
Newtons on meter is joule.
Isn't it? Because remember we were looking at joules and work. And what was the other one? Yeah, what was the other one?
It's Newton per meter too.
Yeah. Okay, so we know force is newtons. Torque.
Wait, pascals? No.
No.
Torque is pascals is pressure. Torque is newtons
Per meter.
Times meter.
times meters.
And it's not joule.
Yeah, what's a joule?
Torque is not a joule. Even though
No.
the units are the
Oh.
same, it's not.
Yeah, that's what we're trying.
Because
Okay.
joules are exclusively for energy. Okay. Come on, seriously. Copy to the buffer. Control paste.
Hello.
Unbelievable. It came back to us, which is good because for some reason I'm not successfully pasting into this. Or if I am, it's pasting somewhere off in the boonies. I don't know. Okay. So since we got that, oh man, do I dare? Do I dare go back and try to use it again as long as you're here, Brittany?
I don't know.
I mean, it's a dangerous game, you know?
I don't know.
I should not be so brutal. She might start to believe, is it really me? But I will tell you, it has never happened when you were not here. Not once.
Yikes.
It's happened now 4 times when you've been here.
Yikes. I don't think I have like any metal or anything in me, so I don't know.
Magnet.
Right?
My parents used to honestly think there might be something about my sister, like, you know, magnetic or something, because her watches just broke constantly.
Oh no.
Heat transfer is Q, right?
Heat times what?
Heat transfer.
No, heat transfer, yeah.
Okay. What food intake will the animal need in one day to replace this heat transfer?
Okay,
So we have 39.7 watts.
Oh.
So in one day, how much energy is it going to lose?
Oh,
That one is per second.
Mm-hmm. Power is equal to the heat over time, or the rate that energy is transferred
so like
over time.
24 divided by like 3600
Not divided, times.
times.
So the energy is going to be the power multiplied by the time, which is what you just said. So we'll put our power, 39.7 watts,
Mhm.
multiplied by 24 hours. That's a 4, the first one. Then multiplied by 30,600 seconds per hour. And that tells us how many joules the animal will have to eat.
And then once we're in joules, what happens?
Joules are energy,
Yeah.
calories are energy. We just need that conversion. Times 10 to the what?
6.
Mm.
Okay, so our conversion factor is the joule equivalent of heat, 1 calorie per 4.186 joules.
Mhm.
Oh yeah. Okay.
I'm going to go ahead and shift that kilocalories per, well, no. I'll leave it. Well, it's 1 kilocalorie per 4.186 joules.
Right.
Because a kilocalorie is a dietary calorie. Because that is what it's asking for, right? Yeah.
819.41.
42.
819. They were added to 820.
Wait, so it's 4.186 kilojoules?
No, it'd be 4.186 kilojoules or 4,186 joules. Since I had joules in my original number, I left the bottom in joules.
Okay.
And so that's why I just erased the decimal.
Okay.
Well, I erased the decimal because it was changing it 3 places. Somebody could listen to this and say, really? That's all you do to go from joules to kilojoules is you erase whatever decimal you have?
So concept this one is
So the concept on this one is just power is the rate at which energy is converted.
But this wouldn't be like this would be like the first half of the test kind of question.
Yeah.
You wouldn't necessarily need. I mean, it's good to know the concept.
Yes, it's good to know that, right? Okay, this next one looks interesting. As always, we're taking life into our hands by trying to copy while Brittany is sitting here.
I'm sorry. I don't know.
It would be funny, but ultimately unfair to say, okay, Brittany, you leave the room now. I'm going to copy another question. All right. The Kilauea volcano in Hawaii is the world's most active, disgorging about 500,000 cubic meters of 1,200 degrees Celsius lava per day. It's a lot of rock coming out of the earth. What is the rate of heat transfer out of Earth by convection? Is this convection?
Yeah.
Yes, it is, because it's a fluid transporting the energy. If this lava has a density of 2,700 kilograms per meter cubed and eventually cools to 30 degrees Celsius, assume that the specific heat of lava is the same as that of granite.
Okay, so we're going to look up the specific heat for that, and it'll be Q equals like sub K multiplied by the specific heat multiplied by the change in temperature, right? That's the equation we'll use when you solve. Maybe not.
Specific heat of Granite is 0.79. 0 joules per gram times Kelvin. Okay, I was looking at that and
you're
didn't.
fine.
What was the rest of the stuff you said?
I was asking if we would use the equation Q equals K multiplied by the specific heat of gravity multiplied by the change in temperature. And that might not even be the right equation. Or it might not even be a equation.
Okay, we're going to use Q as MC delta T. That is the heat that is being deposited on Earth is the mass of the lava times the specific heat of the lava times the change in temperature when it goes from the temperature it leaves the Earth to the Earth temperature.
I said that, except for I don't know why
You
I said K.
use K because you were thinking about, I'm guessing, this K here.
Maybe, yeah.
And so this here is just our standard, specific heat type thing. What is M?
We'll just solve. Crank it out and solve. But why do they give us the...
They gave us the volume and they gave us the density.
Yeah.
So
So
M
then
is equal density
mass
from
divided
volume.
volume.
Oh, wow.
Okay, mass is density times volume. And then we looked up the specific heat and temperature we have, so now we can put it all together.
Okay, so it was asking for the specific heat. It wasn't asking for mass.
To find the mass to be able to do
Do
it.
it.
They gave us the information we need to calculate the mass. So there's our mass, 2,700 kilograms per meter cubed times 5 times 10 to the 5th meters cubed. And then specific heat. And finally, the change in temperature. So we know, once again, heat is going to be leaving the lava. We know the direction. And so I'm just going to put the positive number minus, or the bigger number minus the smaller number to get the magnitude. So I'm going to put my bigger number, 1200 degrees Celsius, minus my smaller number, 30 degrees Celsius. And once again, we know because it's a change in temperature, that's perfectly legit. I don't have to change it to kelvins. If I change it to kelvins, I'd add 273.15 to both numbers, and the 273.15, because it's the difference, we'll subtract out. Yes, ma'am.
Never mind. Wait. Pause. Kilograms and grams.
Oh, she's right. Kilograms and grams. So what do we do to fix that? We erase our decimal, right?
That too.
Now, again, that is changing it by 3 orders of magnitude. It just worked out once again that
1.25 times 10 to the 5th.
Okay, did you do this in kilograms?
Yeah.
So it'd just be times 1,000.
Okay, this number was.
1.25 times 10 to the 18.
We don't have any other.
No, we don't have anything like that. Yeah, it should be times 10 to the 18. Okay, 2.7 times 10 to the 3. 3 plus 5 is 8. Plus 3, 11. Plus 3. What? Oh, wait, it does have megawatts. We're good. 1.25 times 10 to the 15 is what you believe the answer to be, right?
Mm-hmm.
And so that's watts. So now what's a megawatt?
10 to the 6.
Okay. 15 minus 6 is 9. Well, that's still not any of those answers.
Why is it 1200 Celsius? Okay. Yeah, I got 1.247
They're not the same.
to times 10 to the negative 15. I don't know what happened.
Mass divided by 4.
Oh, this is not megawatts.
Or no, instead
What
of
are the units? I feel like a non-genius. What are the units here?
joule.
Joules. What do we have to do to get it into watts?
You have to multiply
Divide by
divide by
seconds?
second.
Yes. And so that's going to be 1.25 times 10 to the 5th joules divided by, and what was the time period for that mass?
Let's see.
1 day.
1 day.
Per day, yeah. Okay.
So we have to divide it by the 24 hours
Times
times
the
3600 seconds per hour. And make sure the 3600 is on bottom when you do your calculation.
1.44.
Times 10 to the 10th. And that's watts. Equals 1.44 times 10 to the 4th megawatts. And so that's not the same as 2. Right? 1.44 and 2 seem to be different numbers,
Yeah.
but that's
What?
the one closest to our answer, and indeed is the one they chose is correct. Yeah, it is odd. It's got to be a rounding issue. Although I looked up the specific heat of granite online, I did not look in the textbook, and maybe the textbook has, their own number that doesn't match the hyperphysics listing for the specific heat of granite.
So concept design is convection.
Merp.
So actually, while this is convection,
Isn't this just heat energy?
we were still doing the heat for change in temperature calculation.
I'm never gonna get this.
Is everyone gonna get to hear our like dumb comments?
Yep.
Yeah, if they want to.
When we were listening last night, I heard my voice. Really?
But they're not dumb comments.
It's all over the internet.
Okay, we got about 10 more minutes.
Okay.
How long have you been holding him hostage?
Oh, it's been only actually in like an hour, 5 minutes. But except for I took like 10 minutes off to go my appointment with the student. So it's not a big deal. It's not like they're a problem.
No. I didn't know how long you'd been camping, that's all.
It's totally fun doing this, don't you think?
Yeah.
What sort of thermal energy do molecules in a solid possess?
Thermal energy that molecules in a solid.
Okay. Okay, so they're not moving very much. So it's not gravitational potential energy sounds kind of ridiculous.
D.
Yeah.
D?
Now, if I am answering this, I am going to be all kinds of technical and say, I'm just going to start drawing over here to the right and assume that when that shows up, it'll be right. There we go. Okay, so I have my molecules, and it's in a solid. So I'm going to just assume it's a crystalline solid. And we have something like this with the fixed positions being very reproducible. What's the difference in a crystalline solid and non-crystalline solid? Non-crystalline solid, the positions of the atoms is not predictable. It appears to be random.
Non-crystal?
So it's non-crystalline, exactly. It's lacking the long-range order. Okay, so these have their fixed positions, but they are going to be vibrating about these positions. And so that vibration includes two types of energy. One is kinetic energy because of the motion, right? 1/2 mv squared. And the other is the potential energy in the bonds. What's holding the atoms in place? What's doing the bonds? Okay, who's taking general chemistry?
We all have.
You all have, okay. What holds the bonds in, or what is the basis for a chemical bond?
Hydrogen, van der Waals, I don't know. Van der Waals forces, hydrogen bonds. That's like the weakest. Like positive and negative charges together.
Charges.
It's the electric force.
Yeah, the electric one.
Right. It's an electromagnetic force. And so you have the change in the separation is going to cause a change in the potential energy associated with electrostatic force. And so we have the vibrational energy has both of those pieces.
Oh, so it is D?
Well, yeah, it is D.
Okay.
But notice you have D is comprised of C plus A.
It is, yeah.
Now, is there gravitational potential energy? Well, there is that too. Nobody ever thinks about that. And when you're calculating the thermal energy, you don't include that. It's not part of the thermal energy. So even though it has gravitational potential energy, that's not part of it. And so I'm pretty sure the answer there is D. It's the vibrational energy. If it was a monatomic ideal gas, then it's only the translational kinetic energy. And yeah, I just checked. I was right. Okay, that's the last.
Was that was the last one for this one?
Actually, the there in this one there's a temperature and kinetic theory problem at the bottom. Oil is heated in a pan on a hot plate. The pan is in thermal equilibrium with the hot plate. These are different people get different questions, so you may not have seen this one. The temperature of the hot plate is 100 degrees Celsius. The oil is at 50 degrees Celsius. Are the pan and oil in thermal equilibrium? And are they in thermal contact? Okay, this is another one that's a fairly short question to answer. So, okay, how did I do that wrong? Oh, yeah, because I clicked the
I'm
copy
here.
button. No, that was my fault. And this is going to look bad, so I got to do it again. Oh, but it crashed anyway.
Told you.
I know, it's like she predicted it. Okay, well, oil is heated in a pan on a hot plate. So here's my pan. It's on a hot plate, so here's the burner underneath. And here's the oil in the pan. So the pan is in thermal equilibrium with the hot plate. What does that mean?
They have the same temperature.
They have the same temperature. Okay, so we have temperature of the hot plate equals temperature of the pan because they're in thermal equilibrium. No heat flows between them because they're the same temperature. The temperature of the hot plate is 100 degrees Celsius. The oil is at 50 degrees Celsius. Are the pan and oil in thermal equilibrium?
No.
You're correct. Why not?
They don't have the same temperature.
Right. Are they in thermal contact?
Yes.
Yes. Why?
Because they're touching. and
They're touching.
and the
So
heat
which
is
mechanism can they transfer through?
Conduction.
Conduction. Because they're in contact, they have conduction open to them. There's not a fluid between them, although oil is a fluid.
Yeah, okay.
And so it's not convection. You could say, well, the pan could heat up air up here. The air could come down. Yeah, you could say that, but that's not going to be a primary form of heating. If you have conduction, you're usually going to ignore the others. Is radiation a possibility? Well, sure. The pan will radiate a little. The oil will probably absorb a little, although the oil is fairly transparent, so it has a very low emissivity, won't do much. But the primary method is conduction. They're in thermal contact through conduction.
Okay, so conduction is two objects touching and transporting heat energy like between each other. Convection is doing it that same thing except it's through fluid, so like through liquid or through air.
Yeah.
And then radiation is
Like by the
sun's
sun.
radiation
Yep.
on a human. There we go.
Yep. It's really cold out. You have a nice window and you sit in the sunlight and you get heated up even though it's cold out because you're receiving radiation from the sun.
Sun's radiation.
I want to like.
What would be? Sorry, go ahead.
I don't know. It's a,
What would be another example besides the sun?
Of okay.
X-rays. Oh.
They are, but no, people don't think of that as heating, even though it is.
Okay.
But you might have a little. Have you seen those heaters that look like fans? It's shaped like it's got a bowl like this, and then it has a heating filament inside.
Probably, I just
Yeah.
can't even think of it.
Well, you see those things, and you walk past them, and you feel an intense heating, and you're like, "What the heck?" And it's not blowing anything, and that's because that bowl-like thing is focusing the waves so that they come out in pretty much just a column. And so when you pass that column, you suddenly feel all of that heat. And so it's like you have your hand really close to it. You're getting the radiation that you would if your hand was really close to it. Or this is an example I usually use in class. When I was a kid, we'd go camping and we joked about making a white man fire. The Indian is at one with nature, makes a small fire, sits close and just gets what he needs and isn't wasteful. The white man makes a huge fire, stands way back, and says, that's you're getting heated by radiation. And I would literally stand like 15 feet from the fire. And the side of me that was facing the fire was so hot I had to like pull my shirt away from my skin. And the side that was away from the fire would just be so cold, I'm shivering. And turn myself around, I was pretty much like a marshmallow. That's an example of radiation, right? Hot air was rising. If you're over that fire, you're getting cooked by the convection. I was to the side, I was getting cooked by radiation. The microwave oven is another example of radiation. The microwave oven was discovered because somebody was working with a microwave system and he put his lunch bag on top of it. And while his sandwich was undisturbed, his chocolate bar was melted. You're like, wait a minute. Yeah, I know, it really is. Anytime you lose chocolate. One of the coolest ways to measure the speed of electromagnetic waves is to put a chocolate bar in a microwave it depends on the microwave, but 10 to 20 seconds. And then you look at where it's melted and it sets up a standing wave which means that you have what we call an antinode, where you have a strong wave and then node, antinode. You can measure the distance from antinode to antinode because you just measure the distance from melted spot to melted spot.
Okay.
And so you can determine the wavelength of the microwaves. And on the back of the microwave oven, it tells you what the frequency is.
Yeah.
And the wave speed is just the frequency times the wavelength.
Do that.
You can. No, not for a lab. You got to make sure you don't have it on as something that rotates, though.
Oh, okay.
You want it to stay, because then you're going to melt multiple places. That's why you have that. So it goes. So each piece of your thing goes through. It's in a node now. It's an anti-node now, and you even out the cooking.
Got it.
That's really cool.
So you'd have to find one of the older ones that doesn't have like the moving plate.
Or you just take the plate out.
Yeah, you just take
Or
the plate
that
out.
too.
Yeah.
That may be easier.
Okay, time to go. I know Nice has something she wants to do here.
No, just